Everyone, I'm Rahul Shandilya. In this lecture on machine learning, we will cover the artificial neural network. We have already covered many portions of this topic earlier. Let's summarize a few important concepts. Artificial neural network is inspired by the biological neural system. We know that our body contains 10 to the power 11 neural spaces cells called neurons, and every neuron is connected with the 10 to the power 4 other neurons. So it is highly massive parallel computing, and it performs some computing much faster than normal processor. For example, image recognition, or face recognition, voice recognition. Although the biological process is slow, but due to its massively parallel architecture, it performs this computation very fast. So artificial neural network is nothing but emulating our biological neural systems in software. So artificial neural network is defined as a neural network. A neural network is a massively parallel distributed processor made up of simple processing units that has a natural propensity for storing experiential knowledge and making it available for use. It resembles the brain in two respects. Knowledge is acquired by the network from its environment through a learning process. Interneuron connection strength, known as synaptic weights, are used to store the acquired knowledge. As we know from study of our biological neuron, that neurons collects its many signals from the dendrite, and the summation of the signal, if cross some threshold, then it's fire a spike signal down the axons, which in turn passes the signal to other neurons, and these interconnections of neurons are synaptic weights. And now we have Hebb's rule that says that the synaptic strength is highly correlated with the firing of the neurons. Similarly, here too, in artificial neural network, we implement the same process. Input signal is weighted, and this weight are varied, changed by the coming data. Now let's see a few characteristics of artificial neural network. Few advantages of artificial neural network. The first one, it is highly non-linear. In fact, it can be both linear or non-linear. A single layer perceptron, as we have already studied, is a linear model, while the multiple layer artificial neural can implement non-linear function, even can implement a discrete function. Second, input-output mapping. It implements input-output mapping, which we done in the supervised learning. Supervised is performed by modification of the synaptic weights by applying a set of label training examples. Adaptivity. Artificial neural networks have built-in capability to adapt their synaptic weights to changes in the surrounding environments. Means even the surrounding is volatile. It has inherent capacity to adapt to this volatile environment. In particular, it can be easily retained to deal with minor changes in the operational environment condition, and it can, once a neuron is trained, it can easily retrain to adapt for some smaller minor changes. Evidential response. By this we mean it provides information not only about which particular pattern to select, but also about the confidence in decision made. This latter information may be used to reject ambiguous pattern and thereby improve the classification performance. We know in complex patterns there are multiple features that are hard to distinguish. So artificial intelligence not only are able to identify the distinguished feature, but also tell you how much it resembles. It tells about the confidence, how much it is confidence that the two patterns are different, and thus it helps in classification it helps in reducing classification error. Contextual information. Every neuron in network is potentially affected by the global activity of other neurons in the network. Consequently, contextual information is dealt with naturally by a neural network. As we know from the architecture that neurons are highly interconnected, so changes in one neuron is easily propagated to others, even further others and further neurons. Fault tolerance. If implemented in hardware form, it is a fault tolerant or capable of robust computation in the sense that its performance degrades gracefully under adverse operating conditions. Conventional hardware or software crash immediately, abruptly when the environment or input is changed. But we humans have some tolerance. So this neural network is also have this tolerance. As we know, this is the mathematical model of neurons, what we call the perceptron. Here easily we can see the input is collected, x1, x2, and it is multiplied by weight and then summed over. This is summing function, and then the sum is passed to some activation functions. If the sum is higher than some threshold value, the output is 1, or the output other than output is 0 or -1. We can note also that one additional bias node. The importance of bias node I will mention later. And on the right, this is the signal flow diagram. It mentions how the signal, the quantity, every node here is the signals, and the branch tells the function we are applying on these signals. So this signal diagram is used for derivation. Now, as we can see easily here, the importance of bias node. If there is no bias node, that means all the signal will pass through 0, and therefore our decision boundary always pass through 0, which is not necessarily true for our practical purpose. So in order to have this constant value in our equations, we put some bias node. Input of bias node is mostly 1. We have already covered the perceptron learning algorithm, but once again let's focus on how the weight is updated. The weight is updated by the previous weight. The next weight, that is weight at n plus 1, is equal to weight at n plus eta. Eta is the learning rate multiplied by difference, that is dn minus yn. Here dn is the desired response and yn is the calculated response. So this eta multiplied by this error is increased into wn. So we can also denote this term as wn. Perceptron is simplest model of our neuron. It is mathematical model of our single neuron. Now it can be combined in different fashion to implement more complicated function by artificial neural network. Perceptron, as we know, is able to classify only linearly classifiable data. When our data becomes non-linear, it fails to classify. So here is the first one is the architecture is simply the number of perceptron stacked over each others, and in this way we can calculate multiple output. Here in the previous architecture the output was only one. Here we can see we can have multiple outputs. Next we can have multi-layer feed forward network. As we can see, there are layers of hidden neurons. Hidden neurons or nodes means that node which is not connected to the output. So multi-layer neural network or layer perceptrons help uh, to implement even nonlinear function, even the discrete function. Now the next architecture is a recurrent network. Here we can see the difference is that in the previous network it was feed forward network. All the signal was only traveling in forward direction. Here we can see the output is feedback into the input of the neuron. This type of network is called recurrent network, and whenever the output is also multiplied with a unit time delay. So whenever we have this feedback loop, that means the circuit, the neurons model have some memory, and this kind of neural network are used in time series data. On the right hand side is also a recurrent network. Here we can see it is a recurrent network with hidden layer, so it can perform both time series data and also implement nonlinear function. Multilayer perceptron are characterized by three important features. The model of each neuron in network includes a nonlinear activation function that is differentiable. The first point is that the activation function is nonlinear, and also the activation function is differentiable. This is an important point. In case of perceptron, we had activation function simply heaviside function, that means which output in only in 1 and 0. Here the activation function must be differentiable. Second, the network contains one or more layers that are hidden from both the input and output nodes, that we call a hidden layer. And third, the network exhibits a high degree of connectivity, the extent of which is determined by synaptic weights of the network. Although multilayer perceptrons implement highly nonlinear, even discrete and complicated functions, the learning process is made more difficult because the search has to be conducted in a much larger space of possible functions, and a choice has to be made between alternative representations of input patterns. In fact, linear function, that is in case of perceptron, had single global minima. In multilayer perceptron, we have multiple local minima. As we can see in this picture, we can easily identify two hidden layers, the first layer and second layer, and every node is connected to all other nodes. In fact, it is not necessary that every node must be connected. That means the weight can be of 0 of value, and also it is not necessary that number of neurons at each layer is same. The architecture of multilayer perceptron depends on which problem we are going to solve. Now the multilayer perceptron is trained using backpropagation algorithm. This is a very important algorithm. In the early history of artificial intelligence, we know that researchers have lost interest in ANN because they thought that multilayer perceptron was they are not able to train the multilayer perceptron, and single layer perceptron are incapable of solving even a slightly complicated functions. But with the advent of backpropagation algorithm, research in ANN was reignited. That's why this algorithm is of utmost importance. So to understand this backpropagation algorithm, we have to understand that these two signals, in ANN network, there are two distinguishable signals. One is called the functional signal. A function signal is an input signal, that is a stimulus that comes in at the input end of the network and propagates forward neuron by neuron through the network, and energy emerges at the output end of the network as an output signal. And the another signal is the error signal. An error signal originates at and output neurons of the network and propagate backwards layer by layer through the network. So in the right side of the diagram we can see the black line shows the forward functional signal, and this blue dotted line shows the backward error signals. So always remember, functions or stimulus is forward, is travel forward, and error is travel backward. Here is the algorithm of backpropagation algorithms. Let's see the steps for the backpropagation algorithm. I have left its derivation for now. In some future lecture, I will derive this backpropagation algorithm. Let's see the step. We can easily distinguish the three steps. The first one, here it is the inputs forward, travel forward from this to this. It is for forward computation, and here we can see that delta's error are these lines shows that error are traveled backward, and according to this the weight are updated finally. So we can distinguish three important part of this backpropagation algorithm. So the input is examples, a set of examples, and each with input vector x and the output vector is y. The network, a multi-layer networks with L layer. So number of layer is L, okay? And the weight Wij is weight, we know, of signal, and activation function is denoted by G. So local variable is delta, which denotes the error, a vector of errors. Indexed by network mode. So the algorithm is very much similar to the perceptron algorithm. Only the difference is that the weight are transferred. One is the forward transfer of stimulus, and the one is the backward transfer of error. And also the formula is different. Little more complicated, which we will derive later. So the let's see. The first step is the weight is initialized with some random numbers. It can be initialized following some normal distributions, and for each node I in the input layer do AI, we transfer the input. For L2 to it is the input layer. Now for the hidden layer we have L is equal to 2. These changes are made in the hidden layer, and this G is the activation functions. The weight is updated using this formula. Now comes to the deep learning. So deep learning is nothing but implementation of multi-layer perceptron in solving complicated problems, in solving the problems which has many phases of operations. For example, in recognition, in face recognition, there are multiple, the problem is solved in multiple stages. For example, one layer solves the edge detection, another layer solves different pattern, different local pattern, and the another layer may solve some global pattern. So deep learning is a class of machine learning algorithm that use multiple layers to progressively extract higher level features from the raw input, for examples in image processing. In deep learning, each level learns to transform its input data into a slightly more abstract and composite representation. Importantly, a deep learning process can learn which features to optimally place in which level on its own. The word deep in deep learning refers to the number of layers that through which data is transformed. More precisely, deep layer systems have substantial credit assignment path CAP. The CAP is the chain of transformation from input to output. That means input is transformed in multiple steps. One layer do one kind of a transformation, the another layer do another kind of transformation. The two important class of deep learning are convolutional neural network, and another is RNN, also known as CNN, convolutional neural network, and another important is the RNN, which we call recurrent neural network. The architect. So we have seen in in CNN is used for face recognition or image recognitions. For extraction, we will see both of these, and RNN have feedback and it is used to process time series data. We will in future, although the detail of both is not important, but in future lecture I will cover these two important architecture.